Hello, everyone. My name is Nick Weithman, and my partner's name is Ryan Goldwasser, and this is our Olentangy Pico Power Project. So this is the location that we decided to design our Pico Power project for. It is one of the weirs along the Olentangy River, just north of campus. This particular location has about a 6-foot drop and is about 100 feet wide. Our rough idea before we move on from this picture of what our project entails is basically putting a Kaplan turbine to catch the water from the top of that weir, directing it through our turbine and drop back down to rejoin the rest of the river. And then the actual generator itself will be over on the right side by that concrete slab, right by that red sign that you see. One of the reasons we chose this specific location is one, because of the availability of that concrete slab to easily store the generator and some of the other equipment associated with it. It's a pretty wide section of the river, and so we're able to tap off enough water to power our equipment, but not enough that it's actually going to alter the flow of the river at all. In addition to all that, there's some residential areas nearby. So the idea being that our unit could be an emergency supply of power in the event of a power outage or something, in order to supply some emergency power to one or two of those larger residential units in the area that you see in the background there. All right, so this was our initial sketch of our project. So initially we were deciding what turbine to use. We decided to go with the Kaplan turbine. So the black portion of the drawing is sort of the structure of our unit, as well as what we call the water ramp. So what catches the water at the top of the weir and directs it through our turbine. The blue part is obviously the water, and then the red portion is the shaft attached to the turbine, and then that circular part at the top is the pulley system. So basically, the idea being the water will go through the turbine, which will drive the shaft. And then as that shaft rotates, it'll be connected via a pulley to the generator off on that concrete slab, which is what's actually going to be generating the electricity. All right, so we created this drawing in SolidWorks. This is our CAD drawing. So we have a close-up on the next slide to show where the actual turbine is and some of the internals of the system. But here you can see that water ramp, which would catch the water at the top of the weir. And then you have the two different sides of the support. So the upper support over on the left would be attached to the top of the weir, and then the lower support legs over on the right side, which would be attached to the bottom of the river, so attached to the ground there. And so the water would come in through the water ramp, go through the guide vanes, which again we'll see better in the close-up. Guide vanes directing the water through the turbine, which drives that shaft, which is the cylindrical portion there, and it will exit via the draft tube. So here's a close-up of the internal workings of the system. So again, we have the Kaplan turbine, which is what we decided to go with. The guide vanes, which are actually attached via their guide vane pins, so that they can be rotated as necessary to maximize the efficiency of the unit. All right, so we actually did end up building a prototype for our system. So over on the left side drawing is an incomplete version, but I wanted to include it so you can see better how sort of the inside of the prototype here. So the support structure being constructed out of wood here, and then the Kaplan turbine is being simulated via a fan from a tower fan. And then over on the right is the completed prototype. So it does not include the shaft or the guide vanes at all, but it does include the water ramp. So you can imagine how that would catch the water at the top of the weir and direct it into the actual turbine itself. So it'd go through the guide vanes, which would be on the top of the water ramp here, and direct it through the turbine. And then once it leaves the turbine, it would be released to the rest of the river flow. So here we built it out of wood and cardboard, but the actual unit itself would be built out of steel, so stainless steel for the actual support structure. The water ramp itself would be sheet metal, because that'd be the easiest to work with, very cost effective. And then the actual internal workings of the system, we would want to use off-the-shelf commercial parts, because that would be the most cost effective, right? So this is a Pico power system, so it would not be economical to build custom parts for this unit, right? So we would find some commercially available parts in order to keep that cost down. All right, so here's some associated calculations. So assumptions that we use. So the Olentangy has a flow rate of about 1,600 cubic feet per second. Converting that over into metric, it's about 45 meters cubed per second. Our system, we estimate, would tap off about a 1 meter wide section of the river at that section, which is about 30 meters wide. So we're estimating that we're going to get about a 30th of the total flow, which equates to 1.5 meters cubed per second. As we mentioned before, the head is about 1 meter. And we are also assuming an efficiency of an overall efficiency of the unit at about 30%. All right, so in order to calculate the power output, power equals efficiency times flow rate times density times the acceleration due to gravity times the head height, which we already gave values for all of those in our assumptions on the previous slide. So power would equal that 0.3 efficiency times 1.5 meters cubed per second times 1,000 kilograms per meter cubed times 9.8 meters per second squared times 1 meter would give us about 4,400 watts, or about 4.4 kilowatts, which is, again, this is a Pico power project, so that's a very reasonable amount, but also a good enough amount that it should be able to supply some emergency power services to one or two of those larger residential units that you saw in the background on the first slide. All right, thank you. That's all we had.